Tonight, we're going to explore something that sounds simple, but is actually one of the deepest questions in modern science. What are the strangest things we have discovered in space? You might imagine distant planets, exploding stars, or black holes swallowing light. And yes, those exist. But the deeper we look, the stranger the universe becomes. Because space is not just big, it behaves in ways that often feel completely unexpected. The universe. You've probably heard that space is mostly empty, that it's cold, dark, and silent, a place where the laws of physics operate in predictable ways. But here's what most people don't realize. Some of the things we've found out there don't just stretch our understanding of physics. They force scientists to re-examine the assumptions that built modern astronomy in the first place. Entire galaxies behaving strangely, stars moving faster than they should, signals appearing where nothing should exist. When you truly grasp it, it changes how you see the night sky. Because those quiet stars above you are not simple points of light, they are clues, evidence, pieces of an enormous cosmic puzzle that scientists are still trying to solve. And by the end of this journey, you're going to understand why the strangest discoveries in space are not just curiosities. They are warnings that the universe may be far more complicated than we once believed. Before we go any further, if you enjoy deep explorations of the cosmos and want to keep discovering mysteries like this, consider subscribing and joining us on future journeys. Now let's dive in. Let's begin with something familiar. Imagine standing outside on a clear night. The air is still. Somewhere in the distance, a faint breeze moves through trees, and the sky stretches above you like a quiet ocean of light. At first glance, the stars appear calm. But the truth is very different. Every point of light you see is a massive sphere of nuclear fire. Most of them are hundreds or thousands of times larger than Earth. Many of them are surrounded by planets. Some of those planets may have oceans, atmospheres, maybe even life. And every second, those stars are moving. Slowly, quietly, but constantly. Astronomers know this because they measure something called parallax. It's one of the oldest and most reliable tools in astronomy. Here's the simple idea. If you hold your finger in front of your face and close one eye, then the other, your finger seems to shift position against the background. That small shift reveals depth. The same trick works with stars. As Earth moves around the Sun during the year, nearby stars appear to shift slightly against the faraway background. By measuring that tiny movement with telescopes, scientists can calculate their distance. It's an elegant method, and it works extremely well. But it also revealed something unexpected. Some stars were not just drifting slowly across the sky. They were racing. In fact, a few were moving so fast that gravity alone shouldn't be able to keep them inside the Milky Way. Picture the center of our galaxy. About 26,000 light-years from Earth lies a region dense with stars, gas, and dust. At the heart of that region sits Sagittarius A star, the supermassive black hole at the center of our galaxy. It contains roughly 4 million times the mass of the Sun. Around it, stars orbit at incredible speeds. Astronomers know this because they track those stars using infrared telescopes that can see through the thick dust clouds surrounding the galactic core. Over many years, they watch the stars trace their paths, point by point. One of those stars completes an orbit in about 16 years. That might sound long, but consider the scale. Its path stretches billions of kilometers across, yet it completes the journey in a time shorter than many human careers. The only explanation is the immense gravity of the black hole pulling on it. And sometimes, when a binary star system wanders too close, something dramatic happens. Imagine two stars orbiting each other like dancers. If they drift near the black hole, its gravity can rip the pair apart. One star is captured, falling deeper into the gravitational well. The other is flung away like a stone from a sling. These are called hypervelocity stars. Some of them travel faster than 5 million kilometers per hour, fast enough to escape the Milky Way completely. For decades, scientists believed such events must be extremely rare. But surveys of the sky began revealing more and more candidates. Large sky mapping projects using wide-field telescopes that repeatedly scan millions of stars track their positions and motions with extraordinary precision. One of the most powerful of these efforts is the Gaia mission, a space telescope launched by the European Space Agency. Gaia measures star positions with accuracy comparable to detecting the width of a human hair from 1,000 kilometers away. Every few months it scans the sky again. And again. And again. From those repeated observations, astronomers build a three-dimensional map of the Milky Way and track how stars move through it. The result is astonishing. Instead of a calm, stellar population drifting gently around the galaxy, the map reveals streams, clusters, and runaway stars racing in strange directions. Some appear to have been thrown out of the galactic centre. Others seem to have been ejected during violent supernova explosions. And a few are so fast that they raise an unsettling question. Where did they really come from? Because not all of them point back to the centre of the Milky Way. Some appear to originate from places where no obvious gravitational slingshot exists, which suggests something even stranger. There may be forces or interactions in our galaxy that we don't fully understand yet. Picture a quiet observatory dome late at night. The telescope turns slowly with a soft mechanical hum. Inside, detectors capture faint starlight that has travelled thousands of years through space. Each photon carries information. Its colour reveals velocity through the Doppler effect, the same principle that changes the pitch of a passing siren. If a star moves toward us, its light shifts slightly bluer. If it moves away, it shifts redder. By measuring that shift, astronomers determine speed. Combine that with Gaia's distance measurements, and you can reconstruct a star's journey through the galaxy. Like tracing the arc of a thrown ball, except the ball is a star, and the throw may have happened millions of years ago. But here's the twist. Some of those stellar trajectories don't just look unusual. They look impossible. Because when scientists run the numbers mass velocity, distance, a few of these stars appear to have been accelerated by something more powerful than the mechanisms we currently understand. Which leads to an uncomfortable possibility. Maybe we haven't discovered all the strange things in space yet. Maybe we've only begun to notice them. And the next discovery, already hiding somewhere in the night sky, might challenge our understanding even more. Because the very next mystery begins not with a star, but with a signal. A radio telescope once heard something that lasted only a few milliseconds, yet in that tiny moment, it released as much energy as the sun emits in days. The implication was unsettling. Something extraordinarily powerful had flashed, then vanished, and the obvious question followed immediately. What could possibly create a signal like that? In 2007, researchers reviewing archived data from the Parkes Radio Telescope in Australia noticed a brief spike buried inside years of observations. The telescope dish stood quietly beneath the southern sky, turning slowly with a low mechanical hum, while computers sifted through streams of radio noise. Most of that noise came from familiar sources, pulsars, satellites, background radiation. But this spike was different. It lasted less than 0.005 of a second. That is shorter than a blink. Yet the signal was bright across a wide range of radio frequencies, and it carried a strange signature. The lower frequencies arrived slightly later than the higher ones. That delay matters. Radio waves slow down when travelling through clouds of charged particles, and the amount of delay tells astronomers how much matter the signal passed through. Think of it like thunder travelling through fog. The thicker the fog, the more the sound spreads and softens. With radio waves, the spreading follows a precise pattern. Scientists call this dispersion, and when they calculated the dispersion of that strange spike, the result implied something extraordinary. The signal had travelled across billions of light years. For a moment, researchers wondered if it was a glitch. Instruments fail. Computers misinterpret noise. Even microwave ovens near telescopes have produced confusing signals in the past. So they checked carefully. They analysed the telescope logs. They examined nearby interference sources. They compared the signal's frequency structure with known artificial transmissions. Nothing matched, which left a startling possibility. The signal had come from outside our galaxy. That first event became known as a fast radio burst, or FRB. The name sounds technical, but the idea is simple. It's a flash of radio energy that appears suddenly, lasts a few milliseconds, and then disappears. At first, scientists assumed it might be a one-time cosmic explosion. Perhaps a neutron star collapsing into a black hole, perhaps two dense stars merging. Events like that are violent, rare, and powerful enough to send enormous energy across the universe. But then something unexpected happened. More bursts appeared. Over the next several years, radio telescopes around the world began detecting similar signals. Each one lasted only milliseconds. Each one showed the same dispersion pattern, suggesting an origin far beyond the Milky Way. And some of them were extremely bright. In fact, during those brief flashes, the energy output rivaled the combined radio emission of hundreds of billions of stars. Picture a quiet desert observatory late at night. A giant radio dish points upward, motionless against a sky filled with stars. Inside a control room, monitors glow softly while data scrolls across screens with faint electronic beeps. Most of the time, nothing unusual happens. But occasionally a burst appears. A vertical spike on a graph. A signal that travelled across cosmic distances only to reach Earth for a fraction of a second. And then vanish. By the early 2000s, astronomers had a puzzle. Fast radio bursts clearly existed, but no one knew what produced them. Then came an even stranger twist. One of them repeated. In 2012, the Arecibo Observatory in Puerto Rico detected an FRB from the same region of sky multiple times. This changed everything. Catastrophic explosions don't repeat. If a star collapses or merges, the event happens once. But this source kept flashing. Weeks passed between bursts, sometimes months. Then another millisecond flash appeared from the exact same location. That meant the object creating the signal survived the event, which narrowed the possibilities dramatically. One leading candidate quickly emerged: magnetars. A magnetar is a type of neutron star, the dense leftover core of a massive star that exploded as a supernova. Neutron stars are already extreme. They pack roughly the mass of the Sun into a sphere only about 20 kilometers wide. Imagine compressing Mount Everest into a teaspoon. That teaspoon would weigh billions of tons. But magnetars go even further. Their magnetic fields are the strongest known in the universe, trillions of times stronger than Earth's. Those fields twist and snap like stressed rubber bands inside the star's crust. When the tension suddenly releases, enormous bursts of energy can erupt. In theory, those magnetic shocks could produce fast radio bursts. But theory alone isn't enough. Astronomers needed proof. To find it, they had to locate exactly where these bursts were coming from. That is harder than it sounds. Most radio telescopes detect signals across wide areas of the sky. Pinpointing the exact source requires multiple instruments working together. So networks of telescopes began coordinating observations. Some systems used interferometry, a technique where signals from several radio dishes are combined to simulate a single giant telescope. By comparing the tiny differences in arrival time between dishes, astronomers can triangulate the source. It's similar to how GPS works. Except instead of satellites calculating your position, radio telescopes calculate the origin of cosmic signals. In 2017, one repeating FRB was finally traced to a small galaxy about 3 billion light-years away. Optical telescopes examined the location and found a compact region filled with young stars. That environment was perfect for magnetars. But the most convincing evidence arrived later. In April of 2020, something remarkable happened inside our own galaxy. A known magnetar called SGR 1935+2 154 suddenly emitted a bright radio flash detected by multiple telescopes on Earth. The signal lasted milliseconds and had the same structure as distant fast radio bursts. The energy was smaller than extragalactic bursts, but the pattern matched. For the first time, astronomers had direct evidence linking magnetars to FRBs. Yet the story didn't end there. Because some fast radio bursts behave in ways magnetars alone struggle to explain. A few produce bursts in tightly spaced clusters. Others show unusual polarization patterns, meaning their radio waves twist through intense magnetic environments before reaching us. One repeating source fires with almost clock-like precision every 16 days. Another repeats every 157 days. Those patterns suggest orbital motion, perhaps involving a companion star or dense environment surrounding the magnetar. Picture a distant galaxy billions of light-years away. A small neutron star spins rapidly inside tangled magnetic fields. Around it, gas clouds swirl while a faint wind of particles streams outward with a soft electromagnetic whisper. Occasionally the magnetic field cracks. A sudden flash erupts. For a few milliseconds, radio waves race outward in all directions, crossing intergalactic space for billions of years until a tiny fraction reaches Earth. And our instruments catch it. But here's the deeper reason these signals matter. They're not just cosmic curiosities, because those dispersion patterns reveal something profound. Every FRB acts like a probe of the universe itself. As the signal travels through space, it passes through clouds of ionized gas scattered between galaxies. That material slightly slows different frequencies. By measuring the delay precisely, scientists can estimate how much matter lies between galaxies. In other words, fast radio bursts allow astronomers to map the invisible structure of the cosmos. For decades, cosmologists suspected that a large fraction of normal matter atoms made of protons and neutrons was missing from observations. Simulations predicted it should exist as thin gas spread through intergalactic space. FARBS are now helping confirm that prediction. Each burst is like a flashlight illuminating the cosmic fog. And the more bursts we detect, the clearer the map becomes. Yet even with these breakthroughs, many mysteries remain. Some FRBs produce energies far beyond what typical magnetar models predict. Others appear in unexpected environments, including older galaxies where magnetars should be rare. Which raises a lingering question. Are magnetars the whole explanation? Or are there multiple kinds of fast radio burst sources hiding across the universe? Some researchers have proposed collisions between neutron stars and black holes. Others suggest exotic plasma structures or unknown astrophysical processes. Every hypothesis makes predictions, and each new detection helps test them. Right now, new observatories like CHIME in Canada scan huge portions of the sky every day, capturing dozens of bursts each year. Quiet arrays of antennas sit beneath open skies, listening continuously with faint electronic whispers. The universe keeps speaking, but the signals last only milliseconds, which means something incredible could happen at any moment and disappear before we even realize it. And if a millisecond flash from across the universe can carry so much energy, then the next strange discovery in space might not be a signal at all. It might be a planet that should never have existed in the first place. A planet was found orbiting a dead star. That alone would be unusual, but the deeper implication was harder to ignore. If the discovery was correct, then a planetary system had survived an event that should have destroyed everything nearby. How could that be possible? In 1992, astronomers Alexander Volschan and Dale Frail were studying a faint, rapidly spinning object known as PSRB 1257+12. The instrument they used was the giant radio telescope at Arecibo Observatory, then one of the most sensitive radio dishes ever built. The dish sat inside a natural limestone depression in Puerto Rico, a vast metal bowl stretching more than 300 meters across. At night, it pointed silently into space while receivers captured faint radio pulses arriving from distant stars. The target they were studying was not a normal star. It was a pulsar. A pulsar is the compact core left behind after a massive star explodes as a supernova. The outer layers of the star are blasted into space, leaving behind an object only about 20 kilometers wide but containing roughly the mass of the Sun. The material inside is compressed so intensely that protons and electrons merge into neutrons. That is why astronomers call it a neutron star. Despite its small size, a neutron star spins extremely fast. Some rotate dozens or even hundreds of times per second. As they spin, beams of radio waves shoot outward from their magnetic poles. If those beams sweep past Earth, we detect them as regular pulses. Picture a lighthouse rotating on a dark coastline. Each time the beam crosses your position, you see a flash of light. Pulsars behave the same way, except the flashes arrive as radio waves rather than visible light. And the timing of those pulses is astonishingly precise. Some pulsars rival atomic clocks in stability. Atomic clocks, which use the vibration frequency of atoms such as cesium or rubidium, are accurate enough that they would lose less than a second over millions of years. Pulsars approach that level of regularity because their rotation is governed by the laws of angular momentum and gravity. But sometimes those pulsars arrive slightly early or late. That tiny shift in timing can reveal something important. If a pulsar has a companion object orbiting it, the pulsar moves slightly toward and away from Earth during the orbit. When it moves closer, the radio pulses arrive a little sooner. When it moves farther away, they arrive a little later. This effect is called timing variation. It's similar to the Doppler shift in sound. A train whistle sounds higher as it approaches and lower as it moves away. With pulsars, the shift appears in the arrival time of the radio pulses rather than their pitch. By measuring those variations with extreme precision, astronomers can detect orbiting planets. That was exactly what Wolfschan and Frail discovered. PSRB 1257 plus 12 had not one planet. It had 3. Each one produced subtle timing signatures in the pulsar's radio pulses. The signals repeated with predictable periods, allowing scientists to calculate their masses and orbital distances. 2 of the planets were roughly similar in mass to Earth, and they orbited very close to the pulsar. At first, the discovery seemed almost unbelievable. A pulsar is born in one of the most violent events in the universe. When a massive star collapses, the resulting supernova releases enormous energy. The expanding shockwave can outshine an entire galaxy for weeks. Nearby planets would be exposed to intense radiation and powerful blasts of matter. Any existing planetary system should be destroyed. Yet these planets were clearly there. Astronomers verified the data repeatedly. Independent observations confirmed the same timing patterns. Over time, the orbital models became more precise. The planets were real, which meant something extraordinary had happened. Either the planets somehow survived the supernova explosion, or they formed afterward from leftover debris. Both possibilities were surprising. Imagine a catastrophic stellar explosion. A shock wave tears through the surrounding system while the core collapses into a neutron star. Material flies outward at thousands of kilometers per second. For a moment, the dying star becomes one of the brightest objects in the galaxy. It seems impossible that delicate planetary orbits could survive such chaos. But there is another possibility. After the explosion, some debris may fall back toward the neutron star. That material could form a rotating disk of gas and dust. Over time, the disk might cool and condense into solid bodies. In other words, a second-generation planetary system. Picture a dense ring of debris circling a neutron star. Small grains collide, stick together, and gradually build larger objects. Millions of years pass. Eventually, planet-sized worlds emerge from the wreckage. Worlds born from a stellar death. Astronomers call this fallback disk formation. And the pulsar planets of PSRB 1257 plus 12 may be the first confirmed example. The idea sounds dramatic, but it follows the same physics that forms ordinary planetary systems. Gravity pulls material together. Collisions create larger bodies. Orbital motion stabilizes the system over time. The difference is the environment. Instead of forming around a warm young star, these planets formed around an ultra-dense remnant with intense radiation and magnetic fields. Conditions unlike anything in our solar system. Later discoveries suggested that pulsar planets are extremely rare. Surveys of many pulsars have found only a few possible candidates. That rarity makes sense. The environment around a neutron star is hostile to planet formation. Yet the fact that even one system exists proves something important. Planet formation is remarkably resilient. Give gravity enough time and material, and it may assemble worlds in places we never expected. In recent years, astronomers have searched for planets around other exotic objects as well. Some orbit white dwarfs, the compact remnants of sun-like stars. Others circle brown dwarfs, objects too small to sustain nuclear fusion. Each discovery pushes the boundaries of where planets can exist. To detect these distant worlds, scientists use several methods. One of the most productive is the transit technique. When a planet passes in front of its star, it blocks a small fraction of the light. Sensitive telescopes measure that dip in brightness. Another method involves radial velocity measurements. As a planet orbits, Its gravity causes the star to wobble slightly. Spectrographs measure tiny shifts in the star's light caused by that motion. But pulsar timing remains one of the most precise detection techniques ever used. A single microsecond shift in pulse arrival time can reveal an Earth-sized planet thousands of light-years away. Inside a radio observatory control room, monitors glow softly while streams of data flow across the screen. Each spike represents another pulse from a distant neutron star. The rhythm is steady, almost hypnotic. Tick, tick, tick. And hidden within that rhythm are tiny variations that reveal entire worlds. Worlds that formed from stellar catastrophe. Yet pulsar planets raise a deeper question. If planets can form in such extreme environments, where else might they exist? Around black holes inside dense star clusters, in regions of space we once thought too violent for stable systems. Astronomers are beginning to suspect that planetary systems may be far more diverse than we imagined. And if that is true, then our solar system may not be the typical example we once believed. But the next strange discovery in space goes even further, because some stars themselves appear to behave in ways that should not be possible. Stars that, according to our models, should already be dead, and yet they keep shining. A star can burn for billions of years, but every star eventually runs out of fuel. That is the rule written into stellar physics, which is why astronomers were puzzled when they found a star that seemed far older than it should be. How could something survive so long? To understand the mystery, we have to step back and look at how stars actually live and die. A star begins its life inside a cloud of gas and dust. Gravity pulls the material inward, compressing it until the pressure and temperature at the center become enormous. Eventually, the core grows hot enough for hydrogen atoms to fuse into helium. Fusion begins. Energy flows outward, balancing the inward pull of gravity. That balance is what keeps a star stable for most of its life. Astronomers call this stage the main sequence. Our Sun is a main sequence star. It has been shining for about 4.5 billion years and will likely continue for roughly another 5 billion. For stars similar to the Sun, this stage lasts the longest. But the process cannot continue forever. Hydrogen in the core gradually runs out. When that happens, the balance between pressure and gravity shifts. The core contracts, temperatures rise, and the outer layers expand. The star becomes a red giant. Eventually, stars like the Sun shed their outer layers and leave behind a dense core known as a white dwarf. Larger stars follow more dramatic paths, ending in supernova explosions and forming neutron stars or black holes. This life cycle is one of the most well-tested models in astronomy. It has been verified by observing millions of stars at different stages of evolution. But occasionally, nature produces something that doesn't quite fit the pattern. One of those cases appeared in a place where astronomers thought stellar evolution was already well understood. A globular cluster. Globular clusters are dense spherical collections of ancient stars orbiting the outer regions of galaxies. Some contain hundreds of thousands of stars packed into a region, only a few dozen light-years across. They are among the oldest structures in the universe. Many formed more than 12 billion years ago, shortly after galaxies themselves began taking shape. Because all the stars in a globular cluster formed at roughly the same time, astronomers can use them as natural laboratories for stellar evolution. If you plot the brightness and temperature of all those stars on a graph called a Hertzsprung-Russell diagram, the pattern reveals how stars of different masses age. Normally, the most massive stars evolve first and leave the main sequence early. Lower mass stars last much longer. But in several globular clusters, astronomers noticed something strange. A small number of stars were hotter and brighter than they should have been. These stars appeared younger than the rest of the cluster, which made no sense. Imagine visiting a retirement community where everyone is roughly the same age. Then you suddenly notice a handful of people who look decades younger than everyone else. Something unusual must have happened. Astronomers named these objects blue stragglers. The term blue refers to their colour, which indicates higher surface temperatures. The word straggler reflects their odd position on the cluster's evolutionary timeline. They should have already evolved into later stages of stellar life. But instead, they appear rejuvenated. For many years, scientists debated what could produce such stars. One possibility involves stellar collisions. Inside the crowded environment of a globular cluster, stars can pass surprisingly close to one another. Over millions of years, gravitational interactions sometimes lead to direct collisions or mergers. When two smaller stars collide, their material combines into a single larger star. The merged object now contains fresh hydrogen fuel, effectively resetting its evolutionary clock. In other words, the star becomes young again. Another explanation involves binary systems. Many stars exist in pairs orbiting each other. If one star expands as it evolves, its outer layers may spill onto its companion. The receiving star gains extra mass and fuel, which can cause it to heat up and shine more brightly. That mass transfer can transform an aging star into something that looks younger and hotter. Observations suggest both mechanisms occur. In some clusters, astronomers see evidence of stellar collisions. In others, they detect binary systems where mass exchange is clearly happening. Either way, blue stragglers reveal something fascinating about stellar environments. Even in systems billions of years old, interactions between stars can reshape their evolution. Picture a dense globular cluster drifting silently through the halo of the Milky Way. Thousands of stars glow softly in a tight sphere. From a distance, it looks calm and peaceful. But inside, the gravitational dance is intense. Stars pass near each other. Binary systems tug and twist through complex orbits. Over millions of years, rare encounters gradually alter the cluster's structure. A faint wind of stellar particles drifts through the region with a whisper of charged dust. And occasionally two stars meet. The result is a single, brighter star that appears far younger than its neighbours. Yet the mystery of stars refusing to die does not end with blue stragglers. Another category of puzzling objects exists in our galaxy. These are stars that should have exploded long ago. Massive stars live fast and die young. Their intense fusion reactions burn through fuel quickly. A star several times heavier than the Sun might survive only tens of millions of years before collapsing in a supernova. But astronomers have discovered stars in certain environments that appear far more massive than the cluster's age should allow. In dense star clusters, repeated mergers between stars may build up extremely massive objects over time. One star merges with another, then another. Each collision adds more material, creating a giant star that did not exist at the cluster's birth. These so-called runaway merger stars can grow far larger than their neighbours. But they are unstable. Radiation pressure inside such stars pushes outward strongly. The balance between gravity and radiation becomes delicate. Stellar winds blow material into space with tremendous force. Some of these stars lose mass so rapidly that they may collapse directly into black holes without a visible supernova. Astronomers study these possibilities using both observations and computer simulations. Large telescopes measure the spectra of cluster stars to determine their temperature, composition, and velocity. Computer models simulate millions of gravitational interactions over time. Together, these tools help reconstruct how clusters evolve. Still, the existence of stars that appear younger than their surroundings reminds us that cosmic systems are rarely simple. The universe loves exceptions, and sometimes those exceptions lead to even stranger discoveries. Because in one nearby galaxy, astronomers recently found something that challenges an entirely different piece of our cosmic model. A galaxy that appears to contain almost no dark matter. Which, if true, could force scientists to rethink one of the most important ideas in modern cosmology. A galaxy should be dominated by something we cannot see. That invisible ingredient is called dark matter. Without it, galaxies should not hold together the way we observe them. So when astronomers reported a galaxy that seemed to lack it almost entirely, the implication was unsettling. Had we misunderstood something fundamental about the universe? To appreciate why this discovery caused such intense debate, we first need to understand why dark matter exists in the first place. When astronomers observe galaxies, they measure how fast stars move within them. One common technique uses spectroscopy. Light from a star spreads into a spectrum, like sunlight passing through a prism. If the star moves toward us, the spectral lines shift slightly toward blue wavelengths. If it moves away, they shift toward red. This Doppler shift allows scientists to measure velocity. By mapping the velocities of stars at different distances from a galaxy's center, Astronomers can build a rotation curve. That curve shows how orbital speed changes with distance. Here is where the puzzle appears. If a galaxy contained only the visible matter we see stars, gas, and dust, the outer stars should move more slowly than the inner ones. Gravity weakens with distance, so orbital speed should gradually decrease. But observations show something very different. In most galaxies, stars far from the centre move just as fast as those closer in. The rotation curve stays flat. Imagine a merry-go-round where riders near the edge spin just as quickly as those near the centre. For that to happen, there must be far more mass in the system than what we can see. That unseen mass is what astronomers call dark matter. The idea was first proposed in the 1930s by Swiss astronomer Fritz Zwicky while studying clusters of galaxies. He noticed that galaxies inside clusters were moving so fast that visible matter alone could not hold them together. Later observations of individual galaxies confirmed the same pattern. Over decades, multiple lines of evidence accumulated. Gravitational lensing showed that massive objects bend light more strongly than visible matter alone would predict. Large-scale surveys mapping millions of galaxies revealed structures that simulations could reproduce only if dark matter existed. Today, the standard cosmological model suggests that about 85% of the matter in the universe is dark matter. It does not emit light. It does not interact with electromagnetic radiation. Its presence is inferred through gravity. Now imagine finding a galaxy where that invisible mass seems almost absent. That is what astronomers believed they had discovered in 2018. The object was called NGC 1052-DF2. It lies roughly 65 million light-years away in the direction of the constellation Cetus. On photographs, the galaxy appears faint and diffuse, like a ghostly smear of starlight spread across space. Researchers studying it use the Keck Observatory in Hawaii, whose twin telescopes sit high on the slopes of Mauna Kea. At night, the domes open slowly with a soft mechanical rumble, revealing mirrors 10 meters wide aimed at the sky. The team focused on small clusters of stars within the galaxy called globular clusters. These clusters orbit the galaxy's center, and by measuring their velocities, astronomers can estimate the galaxy's total mass. If dark matter dominates the galaxy, the clusters should move quickly under the pull of that extra gravity. But the measured velocities were surprisingly low. When scientists calculated the galaxy's mass from those speeds, the result matched almost exactly the mass of its visible stars. In other words, the galaxy seemed to contain little or no dark matter. For many astronomers, this was shocking. Dark matter is thought to act as the gravitational scaffolding for galaxy formation. In computer simulations of the early universe, clouds of dark matter collapse first, creating halos that attract gas. That gas eventually forms stars, producing galaxies embedded inside dark matter halos. Without dark matter, galaxies should struggle to form. So how could NGC 1052-DF2 exist? The discovery quickly sparked debate. Some researchers questioned the distance measurement. If the galaxy were actually closer than estimated, its apparent size and brightness would change, altering the mass calculation. Distance measurements often rely on standard candles objects with known intrinsic brightness. By comparing how bright they appear from Earth, astronomers can estimate how far away they are. One common standard candle is the Cepheid variable star, whose brightness varies in a predictable pattern linked to its true luminosity. But in extremely faint galaxies, finding such stars can be difficult. So scientists examined other indicators, such as the brightness of red giant stars. These stars reach a characteristic maximum luminosity before shedding their outer layers. That point, known as the tip of the red giant branch, can serve as another distance marker. Several independent teams reanalyzed the data. Some supported the original distance estimate. Others suggested the galaxy might indeed be closer, which would reduce the tension with dark matter models. Meanwhile, additional observations revealed another similar galaxy nearby, called NGC 1052-DF4. It also appeared to contain very little dark matter. Two galaxies with the same unusual property were harder to dismiss as measurement errors, which led scientists to explore alternative explanations. One idea involves gravitational interactions. Galaxies do not exist in isolation. They often interact with neighbours, exchanging gas and stars during close encounters. In certain scenarios, a larger galaxy's tidal forces could strip dark matter away from a smaller companion. If the visible stars remain bound together while dark matter is pulled away, the result might resemble a galaxy with little dark matter. Another possibility involves tidal dwarf galaxies. When two large galaxies collide, streams of gas and stars can be flung outward into long tidal tails. Dense regions within those tails may collapse into new dwarf galaxies. Because the material comes mostly from the outer regions of the parent galaxies, it may contain little dark matter. In that case, the unusual galaxies would not challenge dark matter theory, but instead represent a special type of formation. Astronomers continue to study these systems with increasingly sensitive instruments. The Hubble Space Telescope has provided deep images revealing individual stars within the galaxies. By analysing their brightness and distribution, researchers refine distance estimates and mass calculations. Meanwhile, new telescopes such as the James Webb Space Telescope examine faint galaxies in unprecedented detail. Its infrared instruments can detect subtle structures hidden within diffuse systems. Inside a quiet observatory control room, computers display long exposure images slowly building up from faint photons. Each pixel represents light that has travelled tens of millions of years through space. A soft electronic chime marks the completion of another exposure. And within those images, astronomers search for clues. Because whether these galaxies truly lack dark matter or simply appear that way due to complex interactions, the discovery highlights something important. The universe still holds surprises. Even ideas supported by decades of evidence must be tested against new observations. Sometimes those tests confirm our theories. Sometimes they expose their limits. But either way, every strange discovery pushes science forward. And the next mystery waiting in the cosmos may not involve gravity at all. It may involve temperature. Because somewhere in our galaxy lies a region colder than almost anything else in the known universe. A cloud in space holds a temperature colder than most of the universe. Not colder than absolute zero, because that is impossible, but colder than the faint glow left over from the Big Bang itself, which raises a surprising question. How can anything become colder than the background temperature of the universe? To understand this mystery, we need to think about temperature in space. At first glance, a space feels cold simply because there is almost nothing in it. Without air or atmosphere, heat cannot be transferred the way it moves on Earth, yet the universe is not completely frozen. A faint bath of radiation fills every region of space. Astronomers call it the cosmic microwave background. This radiation is the leftover heat from the early universe, roughly 380,000 years after the Big Bang. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, light could not travel freely because it constantly scattered off charged particles. But once neutral atoms formed, light began streaming across the cosmos. That ancient light has been travelling ever since. As the universe expanded, its wavelength stretched. Visible light gradually shifted into microwave radiation. Today, the cosmic microwave background has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. Absolute zero itself is defined as 0 Kelvin, the point where atoms have minimal thermal motion. For decades, astronomers assumed nothing in space could naturally become colder than that background radiation. After all, the cosmic microwave background surrounds everything. Any object colder than it should slowly absorb that radiation and warm up. Yet observations revealed an extraordinary exception. In the constellation Centaurus, about 5,000 light-years from Earth, lies a strange cloud of gas known as the Boomerang Nebula. The name comes from its curved, wing-like appearance in telescope images. At first glance it looks delicate and faint, like a misty shape suspended against the darkness. But inside that cloud, something remarkable is happening. The gas temperature drops to roughly 1 Kelvin. That is nearly 2 degrees colder than the cosmic microwave background. To measure such extreme temperatures, astronomers use radio and millimeter-wave telescopes that detect molecular emissions from cold gas. Different molecules emit radiation at specific frequencies, depending on their temperature and motion. Carbon monoxide, for example, produces spectral lines that shift and broaden depending on the physical conditions of the gas. By analysing those spectral lines, scientists can determine the temperature and velocity of the cloud. Observations from telescopes such as the Atacama Large Millimeter Array in Chile, an array of dozens of antennas spread across a high desert plateau, confirmed the extraordinary coldness of the Boomerang Nebula. At night, the antennas move slowly across the plateau with a soft mechanical hum. Their receivers capture faint signals from molecules drifting through the cloud. Those signals revealed gas expanding outward at astonishing speeds. And that expansion is the key. The Boomerang Nebula formed when a dying star began shedding its outer layers. As the gas rushed away from the star, it expanded rapidly into the surrounding vacuum. Expansion causes cooling. It is the same principle used in refrigeration systems on Earth. When gas expands quickly, its temperature drops. In the nebula, the expansion is so extreme that the gas cools below the temperature of the surrounding universe. Picture a fountain of gas blasting outward into space. The material spreads, thins, and cools as it travels. Inside that expanding envelope, molecules slow their motion until the temperature falls to barely 1 degree above absolute zero. For a brief period in cosmic time, the nebula becomes the coldest natural place known. But the process will not last forever. Eventually the expansion slows, and the cosmic microwave background will gradually warm the gas again. The Boomerang Nebula represents a fleeting stage in stellar evolution. The star at its center is likely transitioning into a planetary nebula, the stage where a sun-like star sheds its outer atmosphere and exposes its hot core. That exposed core will eventually become a white dwarf. White dwarfs are dense stellar remnants roughly the size of Earth, but containing about half the mass of the Sun. Their gravity compresses matter to enormous densities, and they slowly cool over billions of years. Inside the Boomerang Nebula, the dying star is surrounded by an envelope of gas expanding at nearly 160 kilometers per second. That outflow carries enormous energy. Yet it also creates the most extreme natural refrigeration system in the cosmos. Astronomers confirmed the nebula's temperature through several independent measurements. They examined the absorption of microwave background radiation passing through the cloud. They analysed molecular emissions, and they modelled the expansion dynamics of the gas. All methods pointed to the same conclusion. This nebula is colder than the background of the universe, which makes it a fascinating laboratory for studying molecular chemistry at extremely low temperatures. At such conditions, atoms and molecules behave differently. Reactions slow dramatically. Quantum effects become more noticeable. Scientists use similar environments in laboratories on Earth to explore fundamental physics. But replicating the conditions of the Boomerang Nebula on Earth would require elaborate cryogenic equipment. Out there in space, gravity and stellar evolution created it naturally. Picture a quiet region of the galaxy far from bright stars. A faint cloud drifts through darkness, illuminated only by distant starlight. Within the cloud, molecules move so slowly that collisions become rare. A soft whisper of gas expands outward, and for a brief cosmic moment, this place becomes colder than the ancient radiation that fills the universe. Yet the Boomerang Nebula is small on cosmic scales. The next strange discovery we explore is the opposite. Not a tiny cloud, but an enormous region of space. A place where galaxies themselves seem to be missing. A cosmic emptiness so vast that it raises an unsettling possibility. Maybe parts of the universe are far less populated than we expected. A region of the universe contains almost nothing. No bright galaxies, very little matter, just a vast stretch of emptiness. At first that might not sound surprising, because space is mostly empty anyway. But this particular void is so enormous that it challenges how we think large cosmic structures form. How can such a huge region exist? To understand the mystery, we need to look at the universe on its largest scales. When astronomers map the distribution of galaxies across billions of light-years, the universe does not appear random. Instead, it resembles an intricate web. Long filaments of galaxies stretch across space, connecting clusters like strands of glowing thread. Between those filaments lie vast empty regions. These regions are called cosmic voids. The pattern is often described as the cosmic web. Imagine a sponge or foam where dense walls surround empty bubbles. The walls correspond to clusters and filaments of galaxies, while the bubbles represent the voids. This structure formed over billions of years as gravity slowly amplified tiny density variations left over from the early universe. Those variations were first measured in the cosmic microwave background. Satellites such as COBE, WMAP, and later the Planck mission mapped faint temperature differences in that ancient radiation. The variations were incredibly small, only about 1 part in 100,000. Yet they revealed where matter was slightly denser or slightly thinner shortly after the Big Bang. Over time, gravity pulled matter toward the denser regions. Galaxies formed along those growing filaments. Meanwhile, regions with less matter gradually emptied out as material flowed away. The result is the cosmic web we see today. Astronomers study this structure using massive sky surveys. Projects like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies. Each galaxy's distance is estimated through redshift. Redshift measures how much the wavelength of light stretches as the universe expands. The farther away a galaxy is, the more its light shifts toward the red end of the spectrum. By combining position on the sky with redshift distance, scientists can construct a 3-dimensional map of the cosmos. Inside those maps, voids appear as giant cavities between the bright filaments. Most cosmic voids span tens of millions of light-years. Some are larger. But one region discovered in the direction of the constellation Eridanus appears unusually enormous. It is often called the Eridanus supervoid. Estimates suggest it may extend more than 1 billion light-years across. To visualize that scale, remember that the Milky Way galaxy is about 100,000 light-years wide. This void is thousands of times larger. Picture an enormous bubble carved into the cosmic web. Inside it, galaxies exist but are extremely sparse. The density of matter is far lower than the cosmic average. The existence of such a large void raises important questions. According to standard cosmological models, large voids should form naturally as matter flows toward denser regions, but extremely large ones are statistically rare, which makes scientists wonder whether something unusual happened during its formation. The discovery of the Eridanus supervoid is connected to another puzzle known as the cold spot in the cosmic microwave background. When astronomers mapped the microwave background with satellites, they found tiny temperature fluctuations across the sky. Most of these variations match predictions from cosmological theory. But one region appeared noticeably colder than expected. It became known simply as the cold spot. One hypothesis suggests that the cold spot may be linked to the supervoid. When microwave background photons pass through a large underdense region, the expansion of the universe can cause them to lose a small amount of energy. This effect is called the integrated Sachs-Wolf effect. It occurs because gravitational potentials change as the universe expands. Photons traveling through large voids may emerge slightly cooler. If the Eridanus supervoid is large enough, it could contribute to the cold spot observed in microwave background maps. However, the relationship remains uncertain. Some studies suggest the void may not be deep enough to fully explain the temperature anomaly. Others argue that multiple smaller voids along the same line of sight could contribute. Astronomers continue to investigate the region using galaxy surveys and gravitational lensing measurements. Gravitational lensing provides another way to measure mass distribution. Massive objects bend the path of light passing nearby. By analyzing subtle distortions in the shapes of distant galaxies, scientists can infer how matter both visible and dark is distributed along the line of sight. If a region truly lacks matter, lensing signals should be weaker there. Observations so far suggest the Eridanus region indeed contains less matter than surrounding areas, though the exact size and depth of the void remain topics of study. Imagine drifting through that region of space. Galaxies become fewer and farther between. The night sky grows darker as the nearest bright galaxies lie hundreds of millions of light-years away. Only faint, distant clusters appear along the edges of the void. A quiet wind of intergalactic particles moves slowly through the emptiness. And across that immense gulf, light from ancient galaxies continues its long journey toward us. The existence of such vast emptiness reminds us that the universe is not evenly filled with matter. Instead, gravity sculpts enormous structures over cosmic time. Yet even within those structures, surprising extremes appear. But the next strange discovery does not involve emptiness. It involves motion. Because somewhere in our galaxy, a star is moving so fast that it is on a one-way journey out of the Milky Way forever. And the reason for that incredible speed may lead us back to one of the most violent places in the galaxy. A star is racing through the Milky Way at millions of kilometers per hour. Its speed is so extreme that the gravity of our galaxy cannot hold it. Eventually it will drift into the darkness between galaxies, which raises a striking question. What could possibly accelerate a star that fast? Astronomers call these objects hypervelocity stars. The term sounds dramatic, but the physics behind it is very real. Most stars in the Milky Way orbit the galactic center at roughly 200 kilometers per second. That speed keeps them gravitationally bound to the galaxy. But a hypervelocity star travels much faster. Some exceed 1,000 kilometers per second. At those speeds, the star carries enough kinetic energy to escape the gravitational pull of the entire Milky Way. To understand how that happens, we need to look at the center of our galaxy. About 26,000 light-years from Earth lies a region crowded with stars, gas, and dust. Hidden within that dense environment is Sagittarius A star, the supermassive black hole at the heart of the Milky Way. Astronomers cannot see the black hole directly because light cannot escape from it, but they can observe stars orbiting the region around it. Infrared telescopes allow scientists to peer through the thick dust clouds blocking visible light. Facilities such as the Keck Observatory and the Very Large Telescope in Chile track the motions of individual stars year after year. Inside the observatory dome, the telescope rotates slowly with a soft mechanical whisper, while adaptive optic systems correct distortions caused by Earth's atmosphere. On monitors in the control room, bright points trace tiny arcs over time. Those arcs reveal something extraordinary. Several stars orbit the central black hole at tremendous speeds. One of the best-studied stars, known as S2, completes an orbit in about 16 years. At its closest approach, it moves faster than 7,000 kilometers per second. That motion allowed astronomers to measure the mass of Sagittarius A star with remarkable precision. But the black hole does more than just hold stars in orbit. Under certain conditions, it can also fling them away. The mechanism was first proposed in 1988 by astronomer Jack Hills. It involves binary star systems, where two stars orbit each other. Imagine such a pair drifting too close to the supermassive black hole. The intense gravitational field can tear the pair apart. One star may become captured into a tight orbit around the black hole. The other is violently ejected outward, like a stone released from a slingshot. This process is now called the Hills mechanism. The ejected star gains enormous speed during the interaction. Depending on the details of the encounter, it may leave the galaxy entirely. The first confirmed hypervelocity star was discovered in 2005. Astronomers analyzing spectral data from large surveys noticed a star moving away from the Milky Way at extraordinary speed. To measure that velocity, scientists used the Doppler shift of the star's spectral lines. When light from a moving object reaches us, the wavelengths stretch or compress depending on the direction of motion. By examining those shifts carefully, astronomers determined the star's radial velocity at speed along our line of sight. The result was astonishing. The star was moving more than 700 kilometers per second relative to the galaxy. Later observations found even faster examples. Some stars travel at over 1,000 kilometers per second. At that speed, a star could travel from Earth to the Moon in about 6 minutes. Large sky surveys have been essential in finding these rare objects. Projects like the Sloan Digital Sky Survey and the Gaia mission measure positions and motions of millions of stars with unprecedented precision. Gaia, operated by the European Space Agency, scans the entire sky repeatedly. Its instruments track stellar positions with extraordinary accuracy. By comparing observations taken months or years apart, scientists can measure how stars move across the sky. When combined with spectroscopic velocity measurements, these data reveal the full three-dimensional motion of stars through the galaxy. From that information, astronomers can reconstruct their trajectories backward in time. Many hypervelocity stars appear to originate near the galactic center, supporting the Hills mechanism. But not all of them. Some stars seem to come from different regions of the galaxy. That suggests other acceleration mechanisms may also exist. One possibility involves supernova explosions. If two stars orbit each other closely and one explodes as a supernova, the surviving companion may suddenly find itself released from the gravitational pull of its partner. The explosion can propel it outward at tremendous speed. Another possibility involves interactions inside dense star clusters. In crowded clusters, close gravitational encounters between multiple stars can sling one star outward at high velocity. Astronomers test these ideas by studying the properties of hypervelocity stars. Their chemical composition, age, and direction of motion all provide clues about where they came from. For example, a star formed near the galactic center should show chemical signatures typical of that region. A star ejected from a cluster may have different characteristics. Picture a lonely star racing through interstellar space. Behind it lies the spiral arms of the Milky Way. Ahead stretches a vast journey lasting tens of millions of years. The star moves silently through the darkness, carrying whatever planets or debris might remain in its system. No galaxy will capture it again for an unimaginable length of time. Yet these runaway stars are more than just cosmic curiosities. They help astronomers study the gravitational structure of the Milky Way. By tracking their motion, scientists can estimate the distribution of mass in the galaxy, including the invisible dark matter halo surrounding it. If the halo is massive and extended, it may slow escaping stars slightly. If it is lighter, stars may escape more easily. In this way, hypervelocity stars become probes of the galaxy's hidden mass. Inside observatories around the world, computers analyze enormous catalogues of stellar motions. Algorithms search for unusual trajectories. Occasionally a candidate appears on the screen, a star moving far faster than expected. A quiet electronic tone signals a possible discovery. Another runaway star has been found. Yet the universe still holds even stranger objects. Because the next discovery is not merely fast or rare, it is dense beyond imagination. A planet so compressed that its interior may be made largely of crystalline carbon. In other words, a world that may contain enormous quantities of diamond. A planet may exist where much of the interior is crystalline carbon, not scattered gemstones the way we imagine them on Earth, but a vast, compressed structure of diamond-like material, which raises an obvious question. How could a world like that possibly form? The object at the centre of this story lies about 4,000 light-years away in the constellation Serpens. Astronomers call it PSRJ 1719-1438b. At first glance, the name sounds like a string of catalogue numbers, but it hides a remarkable discovery. This planet orbits a pulsar. Just as in the earlier pulsar system we explored, the host star here is a neutron star, the ultra-dense core left behind after a supernova explosion. The pulsar spins rapidly, sending beams of radio waves sweeping across space like a cosmic lighthouse. Each rotation produces a pulse. Those pulses arrive at Earth with astonishing regularity. Radio telescopes detect them as a steady ticking signal. Tick, tick, tick. But sometimes the rhythm shifts slightly. That tiny shift reveals the presence of an orbiting companion. Astronomers detected such variations while studying PSRJ 1719-1438, using radio observatories capable of timing pulses with extreme precision. When researchers analysed the pattern of timing changes, they found a clear periodic signal repeating every 2 hours and 10 minutes. That meant something was orbiting the pulsar, and it was orbiting very close. The distance between the pulsar and its companion is roughly 600,000 kilometres. That may sound large, but on cosmic scales it is extremely tight. For comparison, Earth sits about 150 million kilometres from the Sun. This object circles its host star in less time than a typical movie. Yet despite the close orbit, it remains intact, which immediately suggested something unusual about its composition. If the object were a normal gas giant like Jupiter, tidal forces from the pulsar's gravity would tear it apart. Gas planets cannot survive such intense gravitational stress at such small distances. Instead, the calculations implied an object with enormous density. To estimate that density, astronomers used the orbital parameters derived from pulsar timing. The mass of the pulsar is known to be about 1.4 times that of the Sun. From the orbital period and gravitational equations, scientists could calculate the minimum mass of the companion. It turned out to be roughly the mass of Jupiter. But its size must be much smaller. In fact, the object must be only slightly larger than Earth. That combination, Jupiter's mass compressed into Earth-like size, means the density is extraordinarily high. More than 20 grams per cubic centimetre. For comparison, Arn has a density of about 8 grams per cubic centimetre. Earth's average density is around 5.5. This object is far denser. So what could it be made of? The leading explanation traces the planet's origin back to a star. Long ago, this system likely contained 2 stars orbiting each other. One star eventually collapsed into a neutron star, the other expanded into a red giant. As the giant star grew, its outer layers began spilling onto the neutron star. This process is called mass transfer. Gas from the giant formed a swirling disk around the neutron star before falling inward. Over time, the neutron star spun faster and faster as it accreted material. That process can transform a slow neutron star into a millisecond pulsar, rotating hundreds of times per second. Meanwhile, the donor star gradually lost its outer layers. What remained was the dense core of the star. Stellar cores contain large amounts of carbon and oxygen formed during nuclear fusion inside the original star. As the outer layers were stripped away, the exposed core became smaller and denser. Eventually it may have shrunk to planetary size. At that stage, the object orbiting the pulsar would resemble a crystallized stellar remnant. Under immense pressure, carbon atoms inside the core could arrange into crystalline structures similar to diamond. Not glittering gemstones like those found in jewelry stores, but a vast solid mass of carbon arranged in a diamond-like lattice. Picture a small, incredibly dense world orbiting a neutron star every 2 hours. The pulsar spins rapidly nearby, sending beams of radio waves sweeping across space. Radiation from the neutron star bathes the companion in intense energy. The sky above that world would be dominated by the pulsar itself, a brilliant point of high-energy radiation. And beneath the surface lies material compressed by gravity into one of the hardest substances known. Astronomers sometimes refer to PSR J 1719-1438b informally as the Diamond Planet. Yet the name is more poetic than literal. The interior likely contains carbon in various crystalline states, mixed with heavier elements produced in stellar fusion. The pressure and temperature conditions differ greatly from those that form diamonds inside Earth's mantle. Still, the density calculations strongly suggest a carbon-rich composition. Confirming the details is challenging because the object does not emit its own visible light. Its presence is inferred primarily through pulsar timing measurements. But those measurements are extremely reliable. Pulsar timing can detect variations as small as a few microseconds in pulse arrival times. Over months and years of observation, those tiny shifts build a precise picture of the orbiting object. It is one of the most powerful detection techniques in astrophysics. Inside radio observatories scattered across the globe, receivers capture the pulsar's signals with faint electronic clicks. Data streams into computers that track every pulse with meticulous precision. Each pulse is another heartbeat of the neutron star, and within those heartbeats, scientists read the subtle influence of a tiny but massive companion world. Discoveries like this remind us how diverse planetary systems can be. Some planets orbit ordinary stars like our Sun, others circle white dwarfs or pulsars, a few may be remnants of stars themselves, compressed into dense crystalline forms. Planetary science has expanded far beyond the familiar worlds of our solar system. Yet the next strange discovery in space was once even more mysterious. For years, astronomers detected objects that blinked rhythmically in the sky. Regular flashes of radio waves repeating again and again. At first, no one knew what they were. And for a brief moment in scientific history, some researchers wondered whether the signals might even be artificial. A signal appeared in the sky that blinked with perfect regularity. Every pulse arrived exactly on schedule. No natural phenomenon known at the time behaved that way. And for a brief moment, the question quietly crossed a few scientists' minds. Could it be artificial? The discovery happened in 1967 at the Mullard Radio Astronomy Observatory near Cambridge in England. The facility did not look like the traditional observatories with large domes and mirrors. Instead, it was a vast field filled with thousands of wooden posts and wires stretched between them. Together they formed a radio antenna array. Jocelyn Bell, then a graduate student, was working with her advisor Anthony Hewish to study radio signals from distant astronomical sources. The instrument they built was designed to detect rapid fluctuations in radio emission. Every day, the telescope produced long strips of chart recordings. Pens moved slowly across rolls of paper, marking radio intensity as wavy lines. Bell spent hours examining those charts by eye. One afternoon she noticed something unusual. A tiny patch of scruff, as she described it, appearing at the same place on the chart each day. It lasted only a fraction of a second, but repeated regularly. At first it seemed like interference. Radio telescopes constantly pick up signals from human technology broadcast stations, satellites, radar, but this signal behaved differently. It repeated every 1.33 seconds. Exactly. And it appeared at the same position in the sky as Earth rotated beneath the telescope. That meant the source was astronomical. When Bell and Hewish studied the signal more closely, they found the pulses were incredibly precise. The timing varied by less than 1,000th of a second. No known star or galaxy produced such rapid, regular bursts of radio waves. For a brief period, the researchers jokingly labelled the signal LGM1. The abbreviation stood for Little Green Men. The name was partly humour, but it reflected genuine uncertainty. If an intelligent civilization wanted to send a signal across space, a repeating pulse might be one way to do it. Of course, extraordinary claims require extraordinary evidence. The team quickly searched for alternative explanations. Then another signal appeared. And another. Within months, astronomers discovered multiple sources producing the same kind of rhythmic pulses. That made the extraterrestrial civilization idea extremely unlikely. Nature was responsible, but what kind of natural object could behave like this? The answer soon became clear. These signals came from rapidly rotating neutron stars. Theoretical physicists had predicted neutron stars decades earlier as the remnants of supernova explosions, but until then, no one had directly observed them. The pulses made sense if a neutron star possessed a strong magnetic field tilted relative to its rotation axis. Charged particles would accelerate along those magnetic field lines, producing beams of radio waves. As the star rotated, those beams would sweep through space like lighthouse beams. Each time the beam crossed Earth's line of sight, radio telescopes would detect a pulse. The object had been blinking. Astronomers named them pulsars. Soon after the first discovery, additional pulsars were found across the sky. Some rotated once every second, others spun much faster. A few rotate hundreds of times per second. Imagine an object about 20 kilometers wide spinning that rapidly. The surface speed approaches a significant fraction of the speed of light. Gravity holds the star together with tremendous force, preventing it from tearing apart. The density inside such a star is almost unimaginable. A teaspoon of neutron star material would weigh billions of tons. To confirm the pulsar interpretation, astronomers used several techniques. Radio telescopes measured the pulse periods with high precision. Optical and X-ray observations revealed supernova remnants around some pulsars, linking them to stellar explosions. Theoretical models showed how magnetic fields and rotation could produce the observed radio beams. Everything fit. Over time, pulsars became one of the most useful tools in astrophysics. Because their pulses are so regular, they serve as natural cosmic clocks. Scientists use them to test theories of gravity and to detect gravitational waves. In fact, networks of pulsars spread across the galaxy act like a giant gravitational wave detector. If massive objects such as supermassive black hole pairs warp space-time, the timing of pulsar signals should shift slightly. Astronomers call these networks pulsar timing arrays. By monitoring dozens of pulsars over many years, scientists can detect subtle distortions in space-time itself. In recent years, evidence from these timing arrays has begun hinting at a background of low-frequency gravitational waves produced by merging galaxies across the universe. Once again, an unexpected discovery opened an entirely new field of research. Picture a quiet radio observatory late at night. Antennas point toward the sky, while receivers listen for faint pulses arriving from distant neutron stars. Each pulse crosses thousands of light-years of space before reaching Earth. A soft electronic click marks the arrival. Another cosmic heartbeat recorded. But the story of pulsars also reminds us how easily strange discoveries can challenge our expectations. At first, those blinking signals seemed impossible to explain. Now they are a cornerstone of modern astrophysics. Yet the next strange object we explore stretches our imagination in a different way. Because somewhere beyond our galaxy lies a cloud of gas so enormous that it dwarfs the Milky Way itself. A structure so large that understanding its true size requires thinking on an entirely different cosmic scale. A cloud of gas stretches across a region larger than our galaxy. Not a small nebula drifting inside the Milky Way, but a structure floating between galaxies. Its scale is so enormous that light itself takes millions of years to cross it. Which raises a fascinating question. How can something so large exist without collapsing under its own gravity? The object at the centre of this mystery is called the Slug Nebula. Astronomers discovered it in 2014 while observing a distant region of the universe about 10 billion light-years away. The discovery came from the Keck Observatory in Hawaii, where powerful telescopes study extremely faint objects in the distant cosmos. At night, the domes on Mauna Kea open slowly with a deep metallic hum. Inside, mirrors 10 meters across gather faint light that has travelled for billions of years. Each photon carries a story from the early universe. In this case, the story was unexpected. Researchers were studying a distant quasar. A quasar is an extremely bright object powered by a supermassive black hole, actively feeding on surrounding gas. As matter spirals into the black hole, it heats up and releases enormous energy. Quasars can outshine entire galaxies. Because they are so luminous, quasars illuminate the gas around them. Imagine turning on a powerful flashlight in a dark fog. The beam reveals structures that would otherwise remain invisible. Quasars do something similar on cosmic scales. Using a special instrument designed to detect faint hydrogen emission, astronomers noticed a faint glowing structure surrounding the quasar. At first it appeared small. But as observations continued, the true size became clear. The cloud extended for more than 200,000 light-years. That is roughly twice the diameter of the Milky Way. And that was only the part bright enough to detect easily. Further analysis suggested the structure might extend even farther, potentially approaching 1 million light-years across. To measure such enormous structures, astronomers rely on spectroscopy. Hydrogen gas emits light at a specific wavelength known as the Lyman alpha line. When hydrogen atoms absorb energy and their electrons change energy levels, they release photons at that wavelength. Because the universe is expanding, light from distant objects shifts toward longer wavelengths. This redshift allows astronomers to determine both distance and motion. By mapping Lyman alpha emission across the region, scientists reconstructed the shape of the enormous cloud. The Slug Nebula appeared as a glowing filament of hydrogen gas stretching across intergalactic space. But the real puzzle was density. Intergalactic gas is usually extremely thin, far thinner than the best vacuum chambers on Earth. Yet the brightness of the nebula suggested that parts of the cloud were surprisingly dense. That raised an intriguing possibility. Perhaps the nebula traces a filament of the cosmic web itself. Earlier we discussed the cosmic web structure formed by dark matter and gas. Computer simulations predict that galaxies grow along long filaments, connecting massive clusters. Gas flows through these filaments, feeding star formation in galaxies. But detecting the filaments directly is difficult because the gas is so faint. Quasars may provide the illumination needed to reveal them. In this case, the nearby quasar acts like a cosmic spotlight. Its intense radiation excites the hydrogen gas in the filament, causing it to glow faintly in Lyman alpha light. Without the quasar, the cloud might remain invisible. Imagine an enormous river of gas flowing silently between galaxies. The gas drifts slowly through gravitational valleys created by dark matter. Occasionally it feeds star-forming galaxies along the filament. For billions of years the flow continues, shaping the growth of cosmic structures. The Slug Nebula may be one of the first direct glimpses of that process. However, the discovery also raised another question. The brightness of the nebula seemed too high for the expected density of intergalactic gas. Some astronomers suggested the gas might be clumped into smaller dense pockets that scatter the quasar's radiation. Others proposed that additional sources of radiation, perhaps young galaxies hidden within the cloud, could contribute to the glow. To test these ideas, astronomers used multiple telescopes and instruments. Deep imaging searched for faint galaxies embedded inside the nebula. Spectroscopic observations examined the motion of the gas. Each method added new clues. The results suggest the Slug Nebula likely contains complex structures, dense clumps of gas embedded within larger diffuse regions. Those clumps may represent early stages of galaxy formation. If true, the nebula could be a snapshot of how matter flows through the cosmic web and condenses into galaxies. Picture a vast region of space illuminated by the distant quasar. Filaments of gas stretch across unimaginable distances, glowing faintly like ghostly rivers in the darkness. A soft whisper of intergalactic particles drifts along those filaments. And over millions of years, gravity slowly gathers the gas into new galaxies. Discoveries like this help astronomers understand how the universe built its largest structures. But the next strange discovery challenges something even more fundamental. Not the size of cosmic structures, but the timing of their formation. Because astronomers have found black holes in the early universe that appear far too massive for their age. Objects so large that our current theories struggle to explain how they grew so quickly. A black hole was discovered when the universe was still very young, yet its mass was already enormous, billions of times heavier than the Sun. That scale of growth should require immense time, which leads to an uncomfortable question. How did something so massive form so early? To understand why this discovery surprised astronomers, we first need to think about how black holes grow. A black hole usually begins as the collapsed core of a massive star. When the star exhausts its nuclear fuel, gravity overwhelms the internal pressure supporting the core. The material collapses inward, and if the remaining mass is large enough, the result is a black hole. Most stellar black holes have masses between about 5 and 50 times that of the Sun. But in the centers of galaxies, astronomers find something much larger. Supermassive black holes. These giants can contain millions or even billions of solar masses. Our own galaxy hosts one of them, Sagittarius A star, weighing about 4 million suns. Astronomers measure such masses by tracking the motion of nearby stars or gas. If stars orbit extremely fast near an unseen center, the gravitational pull must come from a very compact and massive object. Infrared telescopes watching the center of the Milky Way have followed individual stars tracing curved paths around Sagittarius A star. Their motion reveals the black hole's mass with remarkable accuracy. But those observations involve a mature galaxy that has existed for billions of years. Now imagine looking much farther away. When we observe distant objects in space, we are also looking back in time. Light from faraway galaxies may have traveled for billions of years before reaching Earth. Astronomers often describe distance in terms of redshift. As the universe expands, the wavelengths of light from distant objects stretch. The greater the redshift, the earlier in cosmic history the light was emitted. In recent decades, telescopes have detected quasars with extremely high redshifts. These quasars are powered by supermassive black holes actively consuming matter. Gas falling toward the black hole forms a swirling accretion disk. Friction inside the disk heats the gas to enormous temperatures, causing it to glow intensely. Some quasars shine brighter than entire galaxies. By studying the spectra of these quasars, astronomers can estimate both their distance and the mass of the black holes powering them. And this is where the puzzle appears. Some of these quasars existed less than 1 billion years after the Big Bang. Yet their black holes already contain billions of solar masses. The growth rate required to reach that size is difficult to explain. Black holes grow mainly through accretion pulling in gas from their surroundings, but there is a limit to how fast this process can occur. That limit is known as the Eddington rate. When gas falls toward a black hole, the radiation produced by the hot accretion disk pushes outward. If the radiation becomes too intense, it pushes gas away, slowing further growth. This creates a natural balance between gravity pulling matter inward and radiation pushing it outward. Under typical conditions, a black hole growing at the Eddington rate doubles its mass roughly every 50 million years. Starting from a stellar black hole of about 10 solar masses, it would take many hundreds of millions of years to reach billions of solar masses. The timeline becomes tight when the universe itself is only a few hundred million years old. One famous example illustrates the problem. A quasar known as ULASJ 1120 plus 0641 lies more than 13 billion light-years away. Observations show that its black hole contains about 2 billion solar masses. Yet the light we see from it left when the universe was only about 770 million years old. That leaves very little time for the black hole to grow. Astronomers have proposed several explanations. One possibility is that the first black holes formed from unusually massive stars. In the early universe, stars may have been much larger than those we see today, containing hundreds of solar masses. When such stars collapsed, they could produce larger seed black holes. Another idea involves direct collapse. Instead of forming from a single star, enormous clouds of gas in the early universe might have collapsed directly into black holes containing tens of thousands of solar masses. Such large seeds would require less growth to reach supermassive size. Simulations suggest this might happen in regions where cooling processes prevent the gas from fragmenting into smaller stars. A third possibility involves periods of rapid accretion exceeding the typical Eddington rate. In certain environments, dense gas flows might allow a black hole to consume material faster than normally expected. Observations continue to test these ideas. Modern telescopes search for early quasars across the sky. Instruments analyze their spectra, measuring emission lines that reveal the motion of gas near the black hole. From the width of those lines, astronomers estimate the gravitational influence of the black hole and calculate its mass. Each new discovery adds another piece to the puzzle. Picture a distant galaxy in the early universe. Gas swirls toward a newly formed black hole, forming a luminous accretion disk. Radiation pours outward, illuminating surrounding clouds with a faint glow. Somewhere in that disk, matter spirals inward with a soft hiss of plasma and magnetic turbulence. Over millions of years, the black hole grows. But the speed of that growth may hold the key to understanding how the first galaxies formed. Because supermassive black holes influence their host galaxies dramatically. Jets and radiation from the accretion disk can heat surrounding gas, regulating star formation and shaping galactic evolution. In other words, these early giants may have played a major role in building the universe we see today. Yet the discovery of such massive black holes so early in cosmic history still leaves astronomers with an open question. Did they grow faster than we expect? Or did they begin much larger than we ever imagined? The answer may lie in another cosmic puzzle. Because when astronomers look across enormous distances, they sometimes notice patterns that should not exist at all. Structures so large and aligned that they challenge our assumptions about how the universe organizes itself. Quasars scattered across the universe should point in random directions. Their orientations depend on the spin of the black holes at their centers, and those spins should be unrelated across billions of light-years. Yet observations have hinted at something unsettling. Some of them appear strangely aligned. To understand why this matters, we first need to think about scale. The observable universe spans roughly 93 billion light-years in diameter. On that scale, structures exist in a hierarchy. Stars form galaxies. Galaxies group into clusters. Clusters connect through filaments of the cosmic web. But according to the standard cosmological model, the universe should become statistically uniform on the larger scales. Cosmologists call this the cosmological principle. It states that when you look at the universe over very large distances, it should appear roughly the same in every direction and location. No preferred directions, no special locations. This assumption is crucial because many models of cosmic evolution rely on it. Yet some observations have hinted at enormous structures that stretch close to the limits of that assumption. One example involves groups of quasars. Quasars are powered by supermassive black holes surrounded by bright accretion disks. The light we see from them often includes polarized radiation, meaning the electric fields of the light waves align in particular directions. Polarization can reveal information about the orientation of the accretion disk and magnetic fields near the black hole. In the late 1990s and early 2000s, astronomers studying quasar polarization noticed something unusual. Over regions spanning billions of light years, many quasars appeared to share similar polarization angles. In other words, their internal orientations seemed correlated across enormous distances. At first, this could have been a statistical coincidence. With enough objects in the sky, random alignments occasionally appear. But as more quasars were measured, the pattern seemed to persist in certain regions. Imagine observing hundreds of distant lighthouses scattered across the ocean. If each lighthouse rotated independently, their beams would point in random directions. Now imagine noticing that many of them point roughly the same way, across thousands of kilometers. That is roughly the scale of the puzzle astronomers faced. Some researchers proposed that large-scale cosmic magnetic fields might influence quasar alignment. Others suggested that the structures of the cosmic web could shape galaxy rotation during formation. If galaxies formed along long filaments of gas and dark matter, their angular momentum might become partially aligned. That alignment could propagate to the central black holes and their accretion disks. However, the distances involved in the observed correlations seemed extremely large. Billions of light years. Such scales push the limits of what current cosmological models predict for coherent structure. Astronomers approached the problem carefully. First, they examined whether observational bias could explain the pattern. Perhaps the instruments measuring polarization introduced systematic errors, or perhaps dust between galaxies altered the polarization signals. Multiple independent studies attempted to rule out these possibilities. Observations from different telescopes and instruments continued to explore the effect. The results remain debated. Some analyses suggest the alignments weaken with larger datasets. Others still find hints of large-scale correlations. The situation illustrates an important part of scientific discovery. Sometimes observations produce patterns that are intriguing but not yet conclusive. They force scientists to gather more data, refine measurement techniques, and test competing explanations. Imagine an observatory perched high on a mountain plateau. The night air is thin and quiet. A telescope slowly tilts toward a distant quasar billions of light years away. Inside the instrument, light splits into its component wavelengths and polarization states. Sensitive detectors measure the orientation of those faint signals. Each observation adds another data point. Another clue. Another attempt to understand whether the universe truly contains patterns spanning unimaginable distances. Even if the alignments eventually turn out to be statistical coincidences, the investigation itself pushes observational techniques forward. Astronomers now measure polarization for thousands of distant objects, building detailed catalogues of cosmic magnetic fields and galaxy orientations. And sometimes the search for one mystery reveals another. Because the next strange phenomenon we explore is not about orientation or structure. It is about light itself, a faint glow that fills the entire universe. Radiation that has been traveling toward us since the cosmos was only a few 100,000 years old. The oldest light we can see. Every direction in the sky glows faintly, not with visible light, but with microwave radiation. It is incredibly weak, almost perfectly uniform, and ancient beyond imagination, and it carries a message from the earliest era we can ever observe. Where did that light come from? The answer lies in a moment when the universe was still young. Right after the Big Bang, the universe was extremely hot and dense. Temperatures were so high that atoms could not exist. Matter consisted of a plasma, a mixture of free electrons and atomic nuclei moving at tremendous speeds. In that environment, light struggled to travel far. Photons constantly collided with charged particles. Each collision scattered the light in a new direction. The universe behaved like a dense fog where visibility was almost zero. But as the universe expanded, it cooled. After about 380,000 years, temperatures dropped enough for electrons and protons to combine into neutral hydrogen atoms. This process is called recombination. When neutral atoms formed, something profound happened. Photons could finally travel freely. The fog cleared. The light released at that moment has been traveling across the universe ever since. As space expanded, the wavelengths of that light stretched dramatically. Originally, the radiation was visible or infrared light. Over billions of years, it shifted into the microwave range. Today we call it the cosmic microwave background. The temperature of this background radiation is about 2.7 Kelvin, just a few degrees above absolute zero. It fills every region of space almost perfectly evenly. In fact, the uniformity of the cosmic microwave background was one of the most important discoveries in cosmology. It was first detected accidentally in 1965 by two radio engineers, Arno Penzias and Robert Wilson. They were working with a large horn antenna at Bell Labs designed to study faint radio signals. No matter where they pointed the antenna, they detected a persistent hiss of microwave noise. At first they suspected interference. They checked electronics, examined nearby transmitters, and even cleaned pigeon droppings from inside the antenna, yet the signal remained. Eventually they realized the noise was not coming from Earth. It was coming from the universe itself. Around the same time, physicists at Princeton University were predicting that leftover radiation from the early universe should still exist. When the Bell Labs team learned about this prediction, the mystery suddenly made sense. The hiss they heard was the cosmic microwave background. Later satellites mapped this radiation with incredible precision. In 1989, NASA launched the Cosmic Background Explorer, known as COBE. Its instruments measured the background radiation across the sky and confirmed that its spectrum matched the predictions of the Big Bang model almost perfectly. COBE also detected tiny temperature variations. These variations were extremely small, only about 1 part in 100,000, but they carried enormous significance. Those tiny differences represent the earliest seeds of cosmic structure. Regions that were slightly denser in the early universe eventually attracted more matter through gravity. Over billions of years, those regions grew into galaxies, clusters, and the vast cosmic web. Later missions improved these measurements dramatically. The Wilkinson Microwave Anisotropy Probe, or WMAP, mapped the microwave background with far greater detail. It refined estimates of the universe's age, composition, and geometry. Then in 2009, the European Space Agency launched the Planck satellite. Planck produced the most detailed map of the cosmic microwave background ever created. Its detectors measured temperature variations across the sky with astonishing sensitivity. The map revealed subtle patterns, tiny ripples frozen into the radiation when the universe was less than 500,000 years old. Picture a spacecraft drifting silently in space. Its detectors cooled to near absolute zero to reduce noise. Inside the instrument, faint microwave photons strike sensors with tiny bursts of energy. Each photon began its journey nearly 14 billion years ago. A soft electronic pulse marks its arrival. Another fragment of the universe's earliest light recorded. By analyzing the patterns in this ancient radiation, cosmologists can estimate fundamental properties of the universe. The data reveal that ordinary matter, the atoms that form stars, planets, and people, makes up only about 5% of the cosmic energy budget. Dark matter accounts for roughly 27%. The remaining 68% appears to be dark energy, a mysterious form of energy driving the accelerated expansion of the universe. These conclusions come not from a single measurement, but from multiple lines of evidence: the cosmic microwave background, galaxy surveys, gravitational lensing, and the brightness of distant supernovae used as standard candles. Each method reinforces the others. Yet even with these successes, the cosmic microwave background still holds mysteries. Some anomalies appear in its temperature map features slightly larger or colder than expected. The cold spot we discussed earlier is one example. Whether such anomalies hint at new physics or simply statistical fluctuations remains uncertain. But the cosmic microwave background remains one of the most powerful tools we have for studying the early universe. It is, in a sense, a photograph of the cosmos when it was still an infant, a fossil record of the moment when light first escaped. And yet the discoveries we have explored tonight, from runaway stars to diamond worlds to giant voids, all trace their origins back to the tiny fluctuations visible in that ancient radiation. Those faint ripples eventually grew into everything we see today. But understanding that connection requires stepping back and looking at the bigger picture, because the strangest discoveries in space are not isolated mysteries. They are pieces of a much larger story about how the universe works. Tonight, we've travelled across an unusual landscape of cosmic discoveries. Not just beautiful sights in space, but puzzles, signals, objects that forced astronomers to stop, recheck their calculations, and sometimes rethink how the universe works. When we began, the question sounded simple. What are the strangest things we have discovered in space? But along the way, the answer became something deeper. Because every strange object revealed a limit in our intuition. A star racing fast enough to escape the Milky Way reminded us that gravity can act like a cosmic slingshot. A millisecond radio flash from billions of light years away showed that neutron stars can release staggering bursts of energy. And a planet orbiting a pulsar proved that even a violent supernova does not always erase the possibility of new worlds. Each discovery carried a measurement behind it. Parallax shifts revealing stellar distances, atomic clock precision in pulsar timing, spectral redshift stretching the light of distant galaxies, standard candles measuring cosmic expansion, survey telescopes mapping the structure of millions of galaxies. These methods matter because science does not rely on a single observation. It builds a network of evidence. Numbers that agree, models that survive testing, predictions that match reality, and when something refuses to fit those predictions, that is often when the most interesting discoveries begin. Consider the scale of what we explored. A hypervelocity star travelling more than 1,000 kilometers per second, a nebula cooling to nearly 1 Kelvin, a void hundreds of millions of light years across, a gas filament stretching beyond the size of the Milky Way. Each of those objects exists because of the same underlying laws of physics. Gravity, electromagnetism, quantum mechanics. But the universe applies those laws across distances and energies that the human mind rarely encounters in everyday life. Which is why space so often surprises us. For centuries, humans looked up at the night sky and saw a calm pattern of stars. Ancient observers mapped constellations and imagined mythological figures scattered across the heavens. But we now know those points of light are not fixed decorations. They are moving, evolving, colliding. Entire galaxies drift through space, sometimes merging in slow gravitational dances lasting billions of years. Black holes grow at their centers, gas flows along filaments of the cosmic web, and in rare moments, a supernova briefly outshines its entire galaxy. Step back even farther. Those galaxies themselves emerge from tiny ripples in the cosmic microwave background fluctuations only 1 part in 100,000 in temperature. From those faint variations grew clusters, stars, planets, and eventually observers capable of measuring them. Which brings us to the deeper reason astronomers study strange discoveries. Because anomalies reveal the boundaries of knowledge. Every time scientists encounter something unexpected, a radio burst that should not exist, a galaxy missing dark matter, a black hole too massive for its age, it forces the same process. Measure again. Test again. Refine the model. Sometimes the anomaly disappears once better data arrive. But sometimes it survives. And when it does, our understanding of the universe expands. Picture the night sky once more. The air is quiet. A faint wind moves through distant trees. Above you, the stars appear steady and calm, scattered across a vast darkness. Yet hidden within that darkness are runaway stars leaving our galaxy forever. Cold clouds drifting near absolute zero, pulsars ticking like cosmic clocks, and ancient light that has travelled nearly 14 billion years to reach your eyes. All of it connected. All of it part of the same unfolding cosmic story. The universe is enormous, but it is also measurable. Through careful observation, patient surveys, and instruments sensitive enough to detect the faintest signals, we have begun to understand how its pieces fit together. And yet the strangest part may be this. The atoms inside your body were forged in the hearts of stars long before Earth existed. Carbon, oxygen, iron, all born in stellar furnaces and scattered through space by supernova explosions. In a very literal sense, we are made of ancient stardust. Small, but connected to the universe in a profound way. So the next time you look up at the night sky, remember that the calm pattern of stars hides a cosmos filled with motion, extremes, and mysteries still waiting to be discovered. Somewhere out there tonight, another strange signal may already be travelling toward us, crossing millions or billions of light years. carrying a clue that could change our understanding of the universe again. Good night. And the sky above you is not silent, it is still telling its story.